In this video, I'm going to go over how we created the tournament, the bracket. So the first thing I did is I looked into what needs to go into creating a tournament bracket. And it turns out a tournament bracket is just a tree, something that you would learn in data structures if you haven't taken that yet. So basically a tree is a data structure where you start with a base, basically root, and from that you're branching off into nodes. So at the top, you're going to have a node, and then it's going to split into multiple parts. So you can have a branch going to the left, a branch going down, and a branch going to the right. And then each of those branches is going to stop at another node, and then that node also has branches, so it can also go down to the left, to the right. It could also add diagonally in a direction. You don't necessarily have to have 3 branches every time. You can have as many branches as you want. So I've implemented that data structure down here, and you can see that it's kind of recursive. So the node goes to another node, so you define it recursively. And you traverse the tree by going to its children. So there's functions in here to do that as well. Okay, so now how do we turn a bracket, or how do we implement a bracket as a tree? And so I've done that here in this tournament file. So the first thing we need to do is figure out how many layers of the tree we need. And that's going to be based off the number of competitors and the amount of players per game. So first of all, we need to normalize the competitor count so that it's equal, or it's a multiple of the number of players per game. And so the way we do that is we're checking while the number of competitors modulo the number of players per game is not equal to 0, you're going to add a by. So basically what this means is if I have 4 players playing, but there's 5 players per game, I need to add a by so that in that extra space there's just going to be no one there. It's basically what we're telling the bracket generator. And so let's say we have 5 players and there's 2 players per game. This will work the same way, where in 2 of the games it'll have full players, and in the last game there'll just be a person with a bye. So this is what these 3 lines are doing. And then we figure out the number of rounds based off this math here, which is just the logarithm of the number of competitors divided by the logarithm of the number of players per game, and then you take the ceiling of that. And you can probably find this algorithm somewhere online, or you can just run it a couple times with a few brackets that you've drawn out to make sure that it works. So once we've done that, we want to shuffle the competitors we have so that they're not always going to be playing in the same order. So it's basically a randomization technique. And then our original node is going to be called the champion. So basically what we're doing is we're starting from the inside and going out. So there's at the end of the bracket there will be 1 champion, and then from the champion you're branching off into a left branch and a right branch, which is going to have 1 player each on him. And so basically those 2 players are going to play each other. And then you go down another layer and you have instead of 2 players you now have 4 players. And then you go down another layer and you have 8 players, and so on. So this first one's just making the champion equal to nothing. We'll fill in the champion's name after we've determined the other games. And then the champion node doesn't have any parents, so we just have to equal to null. And then this is just filling in some global constants, which are how many rounds there are, and then the number of unfilled competitors, which is the number of competitors that haven't been inputted into the bracket yet. And so the first function we're going to call is add lower level round game. This is a recursive function that takes the initial node, the number of rounds, and the players per game. So let's go look at what that function does. So if the round number, remember this is cursive, so this is the base case. If the round number is less than or equal to 0, we're just going to do nothing. Otherwise, we're going to, while there is the number of players per game, and there's we haven't filled all the competitors yet, we're going to create a new node, and in that node we're going to create more nodes based off of how many players per game there are. So basically this is just, in each layer we're making the same number of nodes as the number of players per game. So you can think of each node as kind of as a player. That's why it's initialized as player. But so for each round you need the players per game in it. So let's say we set it equal to 2 players per game. Then this is going to have 2 nodes at each level, which makes sense because you need 2 players to play each other at each of those levels. So that's what this recursive function is doing. And it's going to set each of those, so we can grab it later, we're going to give each of those players a parent node and set it equal to its actual parent. And we're going to tell the parent what its children are, basically. And so if the round number is equal to 1, then we're going to increase the number of competitor slots in the bracket. So what this is going to do is just add 1 extra check to make sure that we're not going to run outside the bounds of the array. Okay, so that's that function. And then we're going to traverse the tree now, because basically after this function, all we have is a whole bunch of initial nodes. Like, they don't actually have competitor names in them yet. They're just basically empty strings. So in this one, we're going to actually add the competitors to the empty strings, so we can actually visualize who's supposed to play each other. So that's going to come down here. It's called add competitors to bottom round. And so first we're going to check to make sure that the depth is equal to the number of rounds. So because everything's inverted, if the depth is 0, that's the championship game. So we want the maximum round is our depth, and that'll be basically round 1. So it's kind of confusing there, but it's just inverted. You can think of it as being inverted. And so we'll set the node name equal to the first unfilled competitor, and then we'll remove that competitor from the list. And so for each of the bottom rounds, it's going to be filling in one of the unfilled competitors. So that's how that function works. And then after we've added all the competitors to the round, we'll just print out what the bracket looks like, which is what this pretty print function does. And then we're going to call the getGames function, which will turn the bracket into something we can actually go through and make sure we filled every single game. So we'll go to the game class, and what we see is we're going to have the competitors for this game, which will just be equal to the number of competitors per round. It won't be all of the competitors in the tournament. It'll just be the competitors in this game. We'll have a Boolean to check if it's running. We'll have a Boolean to check if it's complete. So basically we can, if it's not already running and it's not complete, we know we need to send it to a arena client to run the game. And if it is running, we don't want to send it to the to a arena client, but we want to, if that arena client disconnects, we want to be able to set this is running back equal to false. And if the client does return the right status, then we can set the is running equal to false and set the is complete equal to true. We also keep track of the round number in case we need it, and also the game URL. So once the game's completed, we want to be able to see it later. So we'll store that as well. And so the way we make sure that the game hasn't been created before is we check to make all the nodes their parent. So basically we know all the players are in the same game if their parent node is the same. So we'll keep track of the parent node to do comparisons to make sure that we're adding players to the right game and that we're not duplicating games. So then we also have a set winner function, which once the game's completed, the client will tell us, hey, set this person equal to the champion, and it'll update the bracket, so it'll move the person who wins up a notch to the next node. And these contains players just to double check that we're not adding the same player to the same game twice. And this function actually adds them to the list of competitors. So that's a pretty basic class. Let's go back to tournament. So once we get all the games, I just wrote a test function in here to make sure that the set winner works. We'll just set the first competitor in the game equal to the winner because who cares, we're not actually running the game right now. And then we'll pre-print the function again. So that's kind of this whole how all this works. I guess I haven't really gone over what the player class looks like, but you should see it's pretty obvious from here. All we have in it is, I actually don't even need this game link because we're storing it in the game now. We just need the name and the parent node, and it's a pretty basic class. Okay, and we're not using this class anymore because I originally was going to split up 1v1 as its own file, but it turns out the way that this tree is set up is if we go to this main method, we can see we can change the number of players per game as the second parameter here. So I can change this from any value I want, and it'll generate the bracket based off of that, because that's what how the tree is set up. So I'll run this a couple times and show you the pictures of it running in the end of this video. Thanks.